Determine if the given vectors are orthogonal, parallel, or neither. Well, let's see. Let's take a dot product if we're going to check for orthogonal, okay? So check for orthogonal. I'm going to say U dot W. All right, so what does that do? That produces a scalar, right? And how do we do this? We take the first components and we multiply. Negative 3 halves times 6 plus take the second components and multiply. First components multiply plus second components multiply. All right, so what does that give us? That's what? Negative 9 minus 16, so that gives me negative 25, okay? Automatically right here, if I took the dot product in there, not zero, I could say they're not orthogonal. Not orthogonal, okay? Now, the parallel part, let me see if they're parallel or not. Remember that vectors u and v are parallel. If I could write it, or if I could write vector v as some scalar c times vector w, okay? If I could write vector v this way, then they're going to be parallel, those two vectors. Well, let me see. What is vector v, first of all? Let's just write down what vector v is. Vector v is given by the vector with components negative 3 halves, comma, 2. All right. Now, can I rewrite this as some c value, some number c, times vector w? And what is vector w? 6, negative 8. So in other words, can I find some c value? So whenever I multiply c by this, I get back this part, okay? Well, perhaps the easiest way to find a c value, or to not find a c value here, is think about this. Think about what would I have to multiply by? What would I multiply 6 by to give me negative 3 halves? So what does that value of c need to be? 6 times c should give me negative 3 halves, right? 6 times c should give me negative 3 halves. Let's see. So that'll be c is equal to negative 3 halves times 1/6 if I multiply both sides by the reciprocal. So c will be what? Negative 1 over what? 4? All right, let's see if that same value for c works out for the second component in this vector. So negative 8 times c should give me a 2, right? So negative 8 times c should give me a 2. So c is equal to negative 2/8. What does that give me? Negative 1/4. So I came out with the same c value here and here. So what does that mean? That means if I take 1/4 and multiply it by this vector with component 6, negative 8, I should get back what? Negative 3 halves, comma 2. So what is this? This is vector v, isn't it? Because if I distribute to 1/4, I'll get back this, which was vector v. So is v written as a linear as c times vector w? Is v written as c times vector w? Well, yes it is. So what could I say here? I could say that these two vectors are what? Are parallel. If there's not a c that happens with, then they're neither in this case, okay? All right, let's look at part B. Part B. Same directions for part B, but we're going to have two different vectors here. Let's see what these two vectors are. These two vectors are going to look like vector v is equal to 14 times vector I plus 7 times vector j. And vector w this time is going to be negative 7 times I minus 14 times the vector j, like this. All right, for this set of directions, or for these set of directions where determine if they're orthogonal and so forth, it's going to be easiest to write this just in component form. So this will be a vector with components 14, 7, and w will be a vector with components negative 7, negative 14. All right, let's see. I want to see if they're orthogonal, so I'm going to take V dot W. For my dot product, what I'll do is say 14 times negative 7, 14 times negative 7, plus 7 times negative 14, right? Did its calculation. All right. What does that give me? 98 or negative 98 minus 98. All right. 8 and 8's what? 16. 9 and 9 is 18, plus 1 is 19. And then what do we have? 196, and it's what? Negative. All right, so I took the dot product. If the dot product was 0, orthogonal, right? Was my dot product 0? Not hardly. So what could I say right here? I could say they're not orthogonal. Not or, I'm just going to abbreviate here, okay? Not orthogonal. Now you don't have to write that part. I just do it for my own personal notes, okay? All right, so they're not orthogonal. Now, are they parallel? Let me see how I can test to see if they're parallel. Can I write vector V as C times vector W? Well, what is vector V in component form? We said vector V was 14, 7. So let's write 14, 7. All right. Now, can I rewrite this as some kind of C, some scalar C, times vector W? What is vector W? Negative 7, comma, negative 14, right? So, negative 7 times C should give me 14, and negative 14 times C should give me 7, right? So, negative 7 times C, negative 7 times C, it should equal to 14, and negative 14 times C should equal to 7. So what am I trying to do here? I'm just trying to find that C value, right? All right, so if I solve this, I get what? C is equal to negative 2. How about if I solve this one? I get C is equal to negative what? 1/2. Notice we don't have the same C value, right? So what are we saying? There is no C here that I can find where V will equal to C times W, right? So what can I say if there is no C? I could say they're not what? Parallel here. So I could say not parallel. So if they're not orthogonal, not parallel, then they're what? Neither. They are neither. Okay, let's see what's next in the notes. All right, what we have next in the notes is this. We have taken a component, taken a vector and decompose it into its components is what we call it, okay? So we have, let's say that we have some kind of incline here, okay? And we have some kind of weighted object. I don't know, maybe it's even a weight, okay? What's gonna happen with this weight is due to gravity, it's gonna have a force down here. Maybe it's a 100-pound weight, it exerts a force. 100 pounds that way, okay? Let's call that angle theta. And then we'll call this an F vector for force, okay? Get some different colors over here. All right, so if we have an F vector for force there, if I want to decompose this, what we call decompose, I'm going to think of a vector that is orthogonal to this inclined part right here. So in other words, I'm going to draw it to where it makes a right angle there, okay? You'll think of a vector as orthogonal there. And I'm going to think of a vector that is parallel to this inclined plane, but I'm going to put it over here, okay? Think of a vector that is parallel like that. And these two vectors will break down. And what they'll do is they'll go ahead and form two vectors like this, which we could call f subscript of 2 and vector f subscript of 1, okay? And do you agree that if I take f2 and add it to f1, I will get the f vector here? So let's say that. Let's say f2 plus f1 is equal to the f vector, right? And that's basically decomposing it into its components. I could say if I wanted to, then f1 plus f2 is equal to f. Either one of those ways, okay? All right, let's talk about the projection, what we call the projection, okay? Let's suppose we have this. Get another color here. Let's suppose I have a vector, what do they call it here? I want to stay standard with what I put in my notes. Vector v like this, and let's say I have vector w that looks like that, okay? So I have two vectors here. And let's go ahead and call this angle theta right here, okay? I could do a little better theta than that. Ooh, that did not erase good. All right, so let's say we put a theta right there, okay? And let's look at this right here. Let's look at drawing a vector here. Grab another color. That's orthogonal to vector w here. Vector that's orthogonal to vector w. And let's put the tip of it at the tip of vector v like that, okay? And your book calls this vector v2. Vector v subscript of 2. And we say we're going to make it orthogonal there, so we're going to make a right angle. All right. Now they talk about the projection of vector v onto vector w, okay? Now, what this vector looks like, this projection here, it's a vector that's really on top of vector w here, and it goes from the tail of vector v here to the tail of vector v2, okay? And they call this vector v subscript of 1, and then they use this notation. They say that's equal to the projection of vector v onto vector w. Now to think about this projection, what's the easiest way to think about it, your book says, is imagine the sun being here and beaming down rays, and then what kind of shadow does it make? It takes vector v and it projects it onto vector w like that, okay, if the sun's directly ahead. So we call vector v1 the projection of v onto vector w, okay? All right. Another way we can look at this is, instead of having an acute angle right here, I could look at vector v as being over here. Let's draw that picture, okay? Let's draw a picture of, suppose we have a vector, let's say v right here, and this is a vector w like that, and this time my angle theta is in here, okay? All right, now let's take a look at the projection, okay? Well, let's look at coming out like this with vector w, because whenever I look at a projection, whenever I think of the sun shining down here, what's going to happen with my shadow for v? My shadow for v is going to be down in this region, right? Yeah, so my shadow for v is going to be down in that region. So my shadow is going to be here, right? Something like this. So that's going to be vector v subscript of 1. And then the vector that's going to be orthogonal to w, but where the tip of that vector hits the tip of vector v here, it's going to look something like that, okay? And it's going to be orthogonal, so I'm going to draw a right angle right here, okay? And we're going to call that v subscript of 2. All right, now, actually, with this b subscript of 1, I need to complete it. I kind of just went over here and I never put an arrow in it. I'm going to put an arrow because I want that arrow right there for b subscript of 1 to be at the tail of this b subscript of 2. And we said that this was what? This fancy name of v1 here is called the projection of v, onto what? Vector w here, okay? All right. So what I basically did here with these projections is I broke this down into decomposition of vectors. Do y'all agree if I take v1 visually and add it to v2, I will get vector v? So we're saying that what? v1 plus v2 is equal to vector v, right? Could I do the same thing here? Could I say if I start here and add v1 and v2, that'll give me vector v? Sure will, right? Okay. So let's see. What we have next in our notes is this. They tell us how to decompose a vector into orthogonal vectors. Okay, let's see. Let's erase this and let's write this up here. They say if v and w are two non-zero vectors, then number 1 says what? The vector projection of v onto w. The vector projection of v onto w, vector v onto vector w is given by, they call it projection of vector v onto vector w, and they say you calculate this by taking vector v, vector w, or taking a dot product in my numerator, over the magnitude of vector w squared times vector w like that. Okay, so that's the formula for finding a projection of v onto w. So in other words, if I want to find this vector, the projection of v onto w, or this one, projection of v onto w, here's how I calculate it, okay? Then they say for number 2, they say what? To decompose v into vectors v1 and v2 parallel to w and orthogonal to w respectively, we have v1 is equal to, vector v1 is equal to the projection of vector v onto vector w, which they said in part, or number 1 was this, v dot w over the magnitude of w squared times vector w, okay? Then they go on to say, and v2 and v subscript of 2, or vector 2, is equal to v subscript of 1 minus v minus v subscript of 1. Doesn't that make sense over here, what we wrote? What if I subtract v subscript of 1 from both sides? Looks a lot like that, doesn't it? All right, so we're going to use this stuff right here, okay? We're going to use that stuff. Well, let's see. Let's erase all this, get it out the way. And we're going to look at our example. Our example reads, given vector v, which is given by components 4, negative 3, and vector w, which is given by components 2, negative 2, what does it want me to do? Part A says find a projection of vector v onto vector w. Okay, how do I find this projection of vector v onto vector w? Well, I could use this formula right here, right? I could say vector v dot vector W over the magnitude of vector W squared times vector W is what it says, right? Let's do so. V dot W, what is that? 4 times 2, 4 times 2, plus negative 3 times negative 2. Negative 3 times negative 2, all over the magnitude of W squared. What would the magnitude of W be? The square root of 2 squared plus negative 2 squared. But then I need to square that, right? Because that says magnitude squared times vector W. So times what? 2, negative 2. The formula actually looks worse than what it is. Well, let's see. What do I get up top? I get 8 plus 6 is what? 14? How about here? Could I think of the square and the square root undoing each other, basically? So what do I have? 2 squared plus 2 squared, or 4 plus 4, or what? 8 times 2, negative 2. Well, 14 eighths. Let's go ahead and simplify that. If I simplify this, what do I get? 7 what? 7 fourths times 2, negative 2. And what does this give me? How do I multiply a scalar times a vector? I basically just distribute the scalar in and it produces a vector quantity, right? So what's 7 fourths times 2? 7 halves. And what's 7 fourths times negative 2? Negative 7 halves. So what did I just find? I just found a projection of V onto W. There we go. Part B. Let's see what part B says. Let me erase some stuff here. And let's go into part B. Okay, part B says, find vectors v1 and v2 such that v1 is parallel to vector W, v2 is orthogonal to W, and v1 plus v2 is equal to v. Ooh, there's a lot of stuff. Okay, so find vectors v1 and v2 such that v1 is parallel to W. All right. Vector v1. What is that equal to? Think about what we just had up on the board. v1, we had number 2 here to just erased actually, is a what? Projection of vector v onto what? Onto vector W, right? So vector v1 then is what I just found in part A. The projection of v onto W, which was what? 7 halves, comma, negative 7 halves. So I already did the work for that one, okay? What else do they want? They want vector v2, right? Vector v2. According to this, I was told in that statement that v2 is equal to v minus v1. Vector v minus vector v1. Get some of this stuff out of the way. In fact, I just erased what I needed. All right, let's see. So v2 is v. What was vector v? I got to look back at my notes here because I just erased it. And vector v was 4, negative 3 minus v vector v1. What's vector v1? We just said it's this vector, right? 7 halves, comma, negative 7 halves. All right, how do we subtract vectors? We subtract their components, right? So what's 4 minus 7 halves? Well, 4 is really 8 halves. 8 halves minus 7 halves is 1 half, right? Negative 3 minus negative 7 halves is negative 3 plus 7 halves. So negative 3 is what? Negative 6 halves, negative 6 halves, plus 7 halves is what? 1/2. So what do we get here? We get the vector 1/2 comma 1/2. And that is vector V2. All right, let me erase some stuff here and we'll go into the next part. All right, let's see what our next part is. Our next part reads what? Part C. Part C says what? Show that V1 is parallel to W by finding a constant C such that V1 is equal to C. All right, let me write this down. Such that V1 is equal to C times vector W. So show that V1 is parallel to W. Remember it's parallel, if I could write it that way, by finding a value of C such that this is true. All right, so let's start out with V1. What was V1 equal to? V1 was equal to what? 7 halves comma negative 7 halves. We calculated in part A, right? So let me see if I can write this as some constant C times vector W. Now what was vector W? I don't know, I gotta go back to my notes because I had to erase it on this little small board. Oh, I can't wait to get back in the classroom. All right, so what was vector W? Vector W was 2 comma, what, negative 2? So can I find some value of C? Then whenever I multiply by 2, I get 7 halves. And whenever I multiply that value C by negative 2, I get negative 7 halves. Well, let's see. 2 times C should give me 7 halves, right? 2C is equal to 7 halves. And negative 2C should give me negative 7 halves. Negative 2C should give me negative 7 halves. All right, so multiply by the reciprocal, and that gives me what? 7/4. Same thing here, multiply by the reciprocal, and what do you get? 7/4, right? So what do I have? I have V1 can be equal to 7/4, my C value, times 2 comma negative 2, right? So now this is written in the form C times vector what? W. So V1 is equal to C times vector W. And what do they tell me to do here? They tell me to show that V1 is parallel to W by finding a constant C such that it's true. And what is that constant C value? It is what? 7/4. So that's part of my answer, and actually all this is the other part of my answer here for part C. All right, we're going to stop there, and the next lecture is going to be on how we use these for word problems.